And we are live. So, welcome back, everyone. It's a real pleasure today to welcome Trithep Devakul to our quantum mechanics seminar. I met Trithep a while back when he was an undergraduate student at Northeastern. We worked together on a small project using metrics for states. That was a lot of fun. And then he moved to Princeton, where he got his PhD, and now he's a postdoc at MIT. All right, Trithep, please take it away.
Okay, thanks for inviting me today. Adrian, today I'm going to tell you about this recent work with Yves, Shivaji, and Sid. Shivaji's at Princeton, and Yves and Sid are at Oxford. And it's about quantum oscillations. And it's a new mechanism for quantum oscillations that we found. And it's all in this paper if you're interested. So let me first start out by introducing quantum oscillations. So when we have a metal, a 2D metal for simplicity in a magnetic field, it, as we all know, is given by this Hamiltonian, it's just p squared over 2m. You have some chemical potential, and you have a magnetic field. And it's a standard procedure to solve this Hamiltonian, and you find that the energy splits up into a bunch of Landau levels indexed by some integer n. Here, omega is the cyclotron frequency, b over m. And if you look at the spectrum, here, the black lines are the energy levels as a function of magnetic field. If you're fixed at some Fermi energy here, 0, then as a function of field, you see a whole bunch of states that are crossing the Fermi energy. And the idea is that each time you have a state crossing Fermi energy, the state goes from fully occupied to completely unoccupied, and you end up with some signatures in observable quantities. And this happens periodically in 1 over b as you vary the field. And so you see oscillations periodically in 1 over b. And this is sort of what allows for this, for what's called fermiology, or this process of mapping out Fermi surfaces, where you look at quantum oscillations, and just from various properties of the oscillations, you can deduce properties of the Fermi surface. For example, the 1 over b, the period of the oscillations in 1 over b is directly related to this extremal cross-section area of the Fermi surface. It's 2 pi over the total area of the Fermi surface. This just follows from Onsager quantization. From the offset of this oscillation, where the maxima and minima are, you can deduce the Berry phase of this orbit. So if you're in like a Dirac, you have like a Dirac point at the center of your spectrum, and you have some orbits that are going around it, you can tell this topology from the offset of this oscillation. If you look at the oscillation magnitude as a function of temperature, so here I've shown this low energy density of states, which is just the density of states near the Fermi energy weighted by the derivative of the Fermi function. And you can see it's showing strong oscillations, and it peaks whenever you have a state that's crossing the Fermi energy. And if you look at the magnitude of this oscillation as a function of temperature, it follows this well-known Lifshitz-Kossovich form. And from the fitting to this form, you can deduce what you can extract the effective mass of your bands, average over your Fermi surface. So you can get all sorts of valuable information from looking at quantum oscillations. But now this picture only applies to metals where you do have a Fermi surface. It does not apply when you don't have a Fermi surface. And now I just want to mention that more recently, there's also been experiments that seem to show quantum oscillations in insulators. For example, SMB6, YB12, and most recently, which is what inspired some of this work, was in monolayer 1T prime WTE2. And of course, with experiment, you also have the accompanying theory that attempts to explain these oscillations. So this is in insulators. What I'm going to tell you about today is a mechanism by which quantum oscillations can also occur in nodal semimetals, where this Fermi surface area goes to 0, and you have point-like Fermi surfaces. Okay, and if there's any questions, please feel free to interrupt. So brief outline, I'm first going to review some semi-classical quantization, sort of explain why we typically don't really expect to see quantum oscillations in nodal semimetals at when the Fermi energy is set to 0. Then I'll introduce, in quotes, exactly solvable model that exhibits what we call ZQOs, which is these quantum oscillations. Then I'll tell you some numerical results. I'll give you a semi-classical explanation for these quantum oscillations. And finally, I'll tell you about the exact solution for this model. And to end it all, I'll give you some realizations and generalizations of this physics. Okay, so let me start out by reviewing how semi-classical quantization works for electrons in a magnetic field. So here I just have a quadratic dispersion. And as we know, electrons in a magnetic field move along. They move according to these equations of motions. As they're moving, they feel a Lorentz force pushes them along. Their momentum ends up following this equations of motion, and this leads to motion along equal energy contours. So if you put your electron in here, as it's moving, it'll slowly wind around and form a closed loop. And the Bohr-Sommerfeld-Onsager quantization condition for this type of motion is that the total area enclosed in this p-space orbit should be 2 pi times the magnetic field times some integer n plus some offset gamma. In this case, gamma is just a half. But if you have some Berry phase in the middle, then that'll show up in this offset. So the picture is that we have this quadratic band. We have orbits that are associated with different energies. And as we increase magnetic field, these orbits move upwards along this quadratic dispersion. And so if I go back, that gives rise to this Landau fan structure. For the Dirac dispersion, on the other hand, we can consider this Hamiltonian, which is just V times P dot sigma, where sigma are Pauli matrices. And this leads to a 2-band model where you have a single Dirac point at the middle, and the velocity is given by V. Now, if you do the semi-classical quantization for this, you get orbits that go around the Dirac points like this, above and below, and you also have an orbit that sits exactly at 0. So the spectrum you expect is shown here. You have one zero energy eigenstate that sits exactly at equals 0, and you have a bunch of other states that go as square root of b, and times n, where n is the integer labeling the eigenstate. Now, if you're sitting at away from the Fermi energy, away from E equals 0, I mean, then you have states that are crossing periodically in 1 over b, and you get quantum oscillations. But if you're sitting at exactly E equals 0, then you're right on top of this 0 energy eigenstate, and you don't see any states that are crossing the Fermi energy. And so at least you don't expect to see any quantum oscillations at that point. Now, in a real material, you never have a single Dirac cone. You always have a pair of them for symmetry reasons. So you can ask what happens in that case. Now, the naive expectation there is that this semi-classical picture works well when you can consider each Dirac cone as being isolated from the other. And that happens whenever this, the wave functions located near the Dirac cones are localized within some inverse magnetic length of these Dirac cones. So you could say, well, as long as the inverse magnetic length is much smaller than the separation between the two Dirac points, then this description should work well, and we should see the spectrum of each individual Dirac cone. However, as you increase magnetic field, this inverse magnetic length could become large enough that there's significant overlap between these two states, and then you now have to consider both of them, and you'll end up with sort of a positive and like a negative superposition of the two, and the energies will be split. So semi-classically, you say that these states repel due to tunneling between the two Dirac points. So the spectrum that you expect here is at low field, you get this square root of B dispersion that you expect from a single Dirac point. But as you increase the field, they now split up. There's actually two states on top of each other coming from each Dirac point, and then they split up as the field gets large enough. This is the naive expectation. So now I'll tell you about an example where this naive expectation turns out to be wrong. And it's a remarkably simple theory. It's a K.P theory for two Dirac points, and it's just given by this Hamiltonian. So here you have p squared over 2m. That's just the quadratic dispersion. You have, there's some offset, delta over 2. And this is multiplying by tau z, which is a Pauli matrix. So if we just look at this part, this describes the dispersion shown here, which is two parabolic bands that have some overlap, and they touch each other along a circular surface. This is a metal. Now, when you turn V, the second term is Vpy tau y. When you turn V to be non-zero, this gaps out the spectrum whenever Py is non-zero, but where Py is zero, it leaves it degenerate. So that gives you what's shown here, where you used to have a circular touching, but now you gap it out everywhere except for 2 points, and this gives you two Dirac points. And for the remainder of this paper, I'm just going to set m equals to delta is equal to 1. So we really only have one parameter here, which is v. And when you turn v equals to 1, you end up with this limit where you have two isotropic Dirac points. And I'm going to spoil something for you, which is the spectrum that I computed for this dispersion is exactly this v equals to 1 limit of this model. And we don't have quantum oscillations in this limit. Now you can ask, okay, if at v equals 0, we have a metal, we do have quantum oscillations. At v equals to 1, we have the naive expectations correct. We have no quantum oscillations. What happens in between? Do we have quantum oscillations or not? And what this dispersion looks like is we have two very anisotropic looking Dirac points here. So the answer to this, we can just do the calculation. We put this model in a magnetic field. We just replace P by pi, which is P minus the vector potential. And these pi's have some non-trivial commutation relation. You do this, you can solve this numerically just by defining sort of raising and lowering operators using these pi's and just truncating the maximum Landau level at some point and just diagonalizing. And you find the spectrum shown here on the right. So for now, ignore the vertical red lines. So at v equals to 0, you have coming down from the top. These are this is the Landau fan from the whole band, but we also have an electron band, and those gives rise to these states that are coming from the bottom. And so you have a whole bunch of states coming, they're crossing the Fermi energy. You have a bunch of oscillations anytime something crosses the Fermi energy. Now, when you turn V to be non-zero, already you see even V equals 0.1, which is quite small, you see that at low fields, you already have an isolated state, a pair of states at the middle, separated from the rest. And this is sort of your n equals 0 Dirac cone Landau level. But as you increase field, these two states, they sort of split up, and then they intersect each other repeatedly as a function of field. And this is what we call the serpentine motion of these n equals 0 Landau levels. As you increase v, now v equals 0.4, you see there's very well-formed sort of square root of b dispersion at low fields, but there's still some oscillation that remains. And now these red lines, I actually show the crossings of the zero energy states. So even though here it looks like they're exactly at zero, they're actually oscillating about each other. It's just the magnitude of the oscillation becomes very small as you go to low field. And when you go to v equals to 1, there's actually no more crossings anymore. They just monotonically get further and further away from each other. So for as long as v is less than this critical value, v c equals to 1, the quantum oscillations remain. And it's driven by just a single pair of what are the n equals 0 Landau levels that are moving about each other in a serpentine fashion. And this is what we call zeroth Landau level quantum oscillations, or ZQOs. And this physics is going to be what I'm going to talk about for the remainder of this talk.
Trithep, can I ask you a quick question?
Yes.
How much does this analysis rely on the Dirac light crossings being at Cardiff neutrality or particle hole symmetry?
So the crossings are protected by parity symmetry. So that's I'm about to get to that, but the gray and the black lines are different parity eigenstates. So you can perturb this however you want. As long as you preserve parity symmetry, you're not going to be able to gap out these crossings. And later I do consider sort of breaking particle hole symmetry, and that just shifts things around, but you still end up with the oscillations.
What is parity symmetry in this?
Inversion.
Oh, good.
It's tau z, and you flip the momenta.
Great, thank you.
Okay, so here's parity symmetry, and the point here is that each of these crossings is between two opposite parity Landau levels that are crossing, and each of these red lines are what I call magic fields, in the sense that well, something very special happens at each of these magic fields in this model, which is that this Hamiltonian becomes what's called quasi-exactly solvable. I'll mention briefly what that is later, but for now, I just want to point out that there's a very simple expression for these magic fields at which all these crossings happen. So here, this is the zeroth magic field is all the way off to the right. There's the B1, and then here's B2, B3, B4, and so on. Each of these red lines, you have crossings between the zero energy states. And so this Hamiltonian will turn out to be very special, but I just want to point out that this phenomenon is actually more generic. It's the model itself is special, and this model turns out to be quasi-exactly solvable, and I'll tell you about the solution later. But the phenomenon itself doesn't rely on this exact solvability. It's more generic, and I'll explain that to you later. So if we go back to this fermiology, what happens if we try to look at this through the lens of usual quantum oscillations? Again, we can look at the frequency in 1/b. This corresponds to some effective Fermi surface area, where this effective Fermi surface area is related to the v equals 0 Fermi surface area, but it's corrected by some factor 1 minus v squared. If we look at the oscillation magnitude, on the other hand, at low T, or also any temperature where, so there's quite a big energy gap between the zeroth energy eigenstates and the zeroth Landau level, and like the first one and the second one and so on. So if we're in the temperature range where the temperature is smaller than this gap, all our oscillations are going to be dominated by the movement of a single pair of eigenstates. And this is quite different from usual quantum oscillations, where you sort of have states coming from a whole bunch of states that are crossing the Fermi energy at various points. Here you only have two. And so it leads to this type of temperature dependence that is quite different from Lifshitz-Kossovich within this temperature range. Okay, so that's the fan. So now I've shown you that you have all sorts of states that are crossing the Fermi energy. Now I want to show you that indeed these crossings do lead to oscillations in measurable quantities, and I'll just do that by showing you some quick numerical calculations. So first of all, 4-point resistivity. So I just did some numerics using this Python package quant. Just discretize the model, put it on a lattice, run some current through coming in from the left edge here, and going out through the right edge. And then I attach 2 leads to the top edge here, and I measure the voltage difference across that. And if you look at this plot, this is just the voltage difference divided by the current, which is proportional to the resistivity that you would measure from this type of 4-point measurement. And so it's smooth at low fields, but then as you get to higher fields, you see there's a peak here, it goes down. Each of these gray vertical lines are the magic fields where the crossings happen. Each time there's a crossing, there's a peak. You also have some additional details here, which is probably due to some finite size or some other physics, but these peaks are coming from the bulk crossing physics. And so this model has Shubnikov-de Haas oscillations. Moving on, we can also compute the magnetization. You just compute the total energy, you fill up the Fermi C, compute, this is a discretized model, so you just fill up all the states, you compute the energy, look at the derivative with respect to field, gives you the magnetization, and that's shown here. Low fields, you get something smooth, but then as you increase field, you see that at each of these magic fields, you get discontinuity in the magnetization. And I should mention in both of these calculations, I add disorder to the model and I average over the disorder. So that's why things are appearing to be smooth here. You can also look at the susceptibility, which is just the derivative of the magnetization, and that shows a very clear peak at each of these magic fields. Okay, so now let me explain to you what is happening through a semi-classical picture. So here's the spectrum that we have. It's just 2 Dirac points here and here. And if we look at the equal energy contours of this potential, this is what they look like. So this is at 0 energy, but then you see that the low energy directions, rather than it's not isotropic, the low energy directions prefers to go vertically. And I'll get back to why that's important shortly. But what we have here are that the E = 0 orbits in the semi-classical picture are not really orbits. They're orbits in quotes because they're just located at a single point, at the 2 Dirac points. So to get the energy splitting from the semi-classical picture, we need to consider the tunnel splitting between these 2 states. And this is actually related to a problem of electrons in a double well potential in a magnetic field, which was studied a while back by Jane and Kivelson. Let me just review that. So they studied this model where you have electrons in a magnetic field. Big X and big Y here are some rescaled position coordinates. So you have a magnetic field and you have a potential. And this potential Vxy is just given by this, which has minima at two points. And this turns out to be exactly the square of our Dirac dispersion energy. And what you find is that for V greater than or equal to 1, there's a unique classical tunneling trajectory. So there's going to be some classical path for X and Y, and these are going to be complex generally, but the projection onto the real plane of these paths for V greater than or equal to 1 just goes from this one Dirac point to the other. But for V less than 1, there's 2 possible trajectories. So again, these 2 paths, you have a path, you project onto the real plane, you find that rather than having just one path going straight from one to the other, there's 2 paths that one goes to positive Y and the other one goes to negative Y. And these 2 paths both connect your 2 Dirac points. So what does this mean? Well, if you consider your tunneling from along this one path, you have some you have some action associated with that, e to the minus s classical. And what you can show is that the other path is just you end up with the same action, but it's just complex conjugated. And your tunneling amplitude, which is the real part of this classical action, takes on this form, some b star over b, where b star is some function of v. You also have the imaginary part of the action, which is associated with a Aharonov bone phase that you get for moving along these two paths. That's the imaginary part, and it's given by this expression. And now, knowing this, you can sort of compute the tunnel splitting by summing over all these instanton events where you jump from one to the other, back, and so on. And this tunneling splitting is just given by e to the minus the real part of this classical action. But now the imaginary part leads to interference between these two paths, and so you end up with a cosine, some offset, and the imaginary part here. And plugging in what we computed, you get this. So the gap is exponentially small in 1 over b. So as you go to small field, the oscillation magnitude becomes smaller exponentially. But also there's a cosine here. And this, in fact, gives you exactly the periodicity and exactly the location of all the fields where these crossings occur. So the picture for these oscillations is whenever you have two tunneling paths in your dispersion, they can destructively interfere, and that leads to vanishing of the tunneling elements, and that leads to a degeneracy. And this happens periodically in 1 over b. It's like the double slit experiment. You start here, you go up here, but if you also go down there, you could end up with the fact that these two paths interfere completely destructively, and you end up with no tunneling at all. And that's the picture for what's going on and what's leading to these oscillations. Great. So now let me talk about. Okay, so this is the semi-classical picture, but this Hamiltonian is actually more special, which is it has an exact solution. So let me briefly outline how that works. So parts of this spectrum, not the whole spectrum and not at all parameter values, but parts of it can be obtained exactly. And so how does that work? So let me write the Hamiltonian in a slightly different way. So I'm rotating, this used to be tau z, I'm rotating just to sigma x, and this is sigma y. And the reason for that is so that this whole Hamiltonian takes this sort of chiral form where everything lives in the off diagonals. And here little h is given by this. So this term comes from the sigma x part, and then you have this imaginary part that comes from the sigma y. And I can just regroup this such that it looks like this, where you have pi x squared, then you have pi y with an imaginary shift squared, and you have a constant term over here. And this Hamiltonian is easy to solve. It's just a quantum harmonic oscillator in a constant imaginary vector potential. You can also think of it as an imaginary shift, but it's a non-Hermitian Hamiltonian, but it turns out to have all real eigenvalues, and you can solve its eigenstates exactly. It's just given by this. This is just the harmonic oscillator part, and this is just the constant offset. Now, knowing the eigenvalues of h, the eigenstates and eigenvalues of little h doesn't immediately tell you the eigenvalues of big H, unless that is the eigenvalue is 0. So suppose that we have some eigenstate phi n of little h that is of eigenvalue 0. Then we can construct this eigenstate where you put this phi n on the top and it's 0 on the bottom, and you can plug this in. You act on this with h. This one just gets acted on by little h, and it becomes 0. So this state psi is an exact E equals 0 eigenstate of big H. So when does this happen? So this happens whenever we have a 0 eigenstate of little h. So solving whenever lambda n equals to 0 as a function of field, you find that this happens whenever the field is given by b equals to bn, which is exactly the formula we derive for the magic fields. So the H only has 0 energy eigenstates whenever B is this particular values. Right. So at the magic field Bn, we have 2 exact E equals 0 eigenstates, and they're given by this form. We can ask what they look like, and you can do that by computing the Husimi function, which is just the overlap of the state phi n with a coherent state that's localized at some momentum pi x pi y. And this takes on this simple form where you just have some polynomial in pi x and pi y raised to the nth power, and there's a Gaussian, and they're shifted. This is shifted by plus v, and this is shifted by minus v. And if I just plot this as a function of the field, that's what I've shown here. So at low fields, you see that the states are well localized around the Dirac point. This is the Husimi function for state phi n. It's located on the right Dirac point here. And as you increase field, it sort of gets larger, and it sort of spreads out anisotropically, and it sort of forms this banana shape, which is in agreement with our picture of these states being sort of at the Dirac points, but then they're spreading along the low energy contours, low energy directions of this dispersion. And if you do the same thing for the state phi bar, that gives you the same picture, but it's just flipped. And so this state is localized on the other Dirac point. This state is localized on the right Dirac point. So this is the 0 energy eigenstate, but this Hamiltonian ends up having more structure than that, which is if you're sitting at a magic field Bn, and you look at the Hamiltonian in this basis of eigenstates of little h, phi n or phi bar n. Now recall that little h is non-Hermitian, so this is a non-orthonormal basis, but h has some block structure in this basis. And so what you can do is you can just solve these you can solve this block diagonalizing just find the eigenvalues of just a n plus 1 dimensional finite matrix. And you find exactly, and the proof of this is in the paper, but you find exactly n plus 1 exactly degenerate pairs of exactly solvable states for a total of 2n plus 1. So here, this is the full spectrum, and I've marked the red lines of the magic fields, and the red points are the exactly solvable eigenstates. So here, there's the sort of the zeroth magic field. There's only these 2 states that you can solve for exactly at e equals 0. But once you go to the next magic field, you again have these 0 energy states. They're always there, but now you have 2 crossings. You have a crossing that occurs at positive energy here, and another crossing that occurs down there. And these states can be solved for exactly by diagonalizing a finite matrix. You go to B2, the next magic field, you end up with this. You have 2 more. Now you have a total of 1, 2, 3, 4, 5 crossing pairs, and they give you the degenerate. They give you can solve these eigenstates exactly, and they give you degenerate pairs of eigenstates. Okay. From the exact solution, we can also learn about the oscillation magnitude. So we can sit at a magic field and we can perturb about it to estimate the slope of so we sit at a magic field and we perturb slightly about it, and we can estimate the magnitude of the oscillations from that. So E takes on this form. The E of the 0th Landau level eigenstates are plus or minus some function curly E of B times the oscillating part, where this is the oscillation magnitude. And you compute it exactly. It takes on this form. There's some hypergeometric function. It's not particularly nice in this form, but you can look at what it does asymptotically when B is much less than B naught, where B naught here is the sort of the 0th magic field. So it turns out that there's 2 different asymptotic regimes. You can be where V is much less than V squared, or when V is not much less than V squared, but still less than B naught. and they have these two different forms. Here there's a Bessel function, and for v, b much less than v squared, you have this form where it's just an exponential, and it goes as e to the minus b star over b, which, if you recall, is exactly what the semi-classical analysis predicted. But now we have even more information, right? We have the prefactor. The prefactor is not very straightforward to compute in the semi-classical analysis, but here we have it exactly. And we also have, I mean, this is the exact expression which is valid, even when b is not small, where the semi-classics are limited to. Okay, so before I move on, I just want to briefly mention that this model is actually related to the Rabi model in a very fundamental way. So the quantum Rabi model describes a qubit interacting with a photon. So it's just this Hamiltonian. You have the delta R, which is the qubit energy gap. You have omega, which is the energy of your photons, and you have some coupling G, which allows your qubit to flip while emitting or absorbing a photon. And if you write this Schrodinger equation for the Rabi model, and you look at it side by side with the Schrodinger equation for our Hamiltonian H, you find that they can be mapped exactly to each other given this mapping. And the important part, the thing I want to point out about this is that the parameter here, delta R, is a parameter of the Rabi model, but here it gets mapped onto E, which is the energy of our model. So it's not like the Hamiltonian can't be mapped to one another, but the Schrodinger equations can, and they involve an interchange of parameters and energy. And also this coupling parameter G in the Rabi model is mapped onto I times V times square root of B over 2. So G, if we want to equate these two, G has to be imaginary. So you can think of our model as sort of an analytic continuation of the Rabi model to imaginary G. And the reason that's possible so both H and the Rabi model are Hermitian. So you might imagine, how can you analytically continue it to imaginary values of the coupling while also being a Hermitian model? That's because this mapping involves interchanging energy with parameters. The analytic structure of this Rabi model has been well studied. The exact solution of the eigenstates that we found were originally found. They're called the Juddian isolated exact solutions in the math literature, and they're found way back by Judd. And the properties of the other eigenstates beyond these solutions have also been solved by Brock, and there's a recent review by Xie, Batchelor, and Lee, which shown here, if you're interested. Right. So, and again, I just want to point out that although this model is very fine-tuned, the phenomenon itself is not. And we can see by adding various perturbations to our model. So we can consider, for example, if the original structure didn't have particle hole symmetry, if the electron mass is not equal to the hole mass, this is what the spectrum. I'm just focusing on the zero energy eigenstates. The spectrum again looks the same, but it's just slightly shifted up. And here the blue line is the Fermi energy, which I fixed at charge neutrality. You can also consider symmetry which breaks parity. So, for example, a Dirac mass term. This just gaps out the states at zero energy, and you don't have any states crossing Fermi energy anymore. Now you could still have quantum oscillations, say from modulation of the energy gap as a function of field, but they're not going to be as sharp as if you actually had states crossing the Fermi energy. You can also consider adding a Haldane mass, which gaps out which gaps out your band structure, but it does so in a special way, such that both of these states they get shifted to positive energy. And if you're still fixed at charge neutrality, then your Fermi energy still lies between them, and you do end up with oscillations that remain. Now you can also consider a generalization of our model where we add spin degrees of freedom, and now we're allowed to add a Kane-Meillet mass term, which turns our system into a spin Hall insulator. And so that's what's shown here. You now have two copies of the Haldane mass, but with different signs. And so now your Fermi energy is just at 0. And at low fields, you don't have any states crossing Fermi energy. But it's possible that once you go to a certain high enough field, this oscillation magnitude will be larger than the gap, the shift at which they've been pushed to, and you do end up with states crossing, and you could end up with some weird features that's going on as a result of that. Okay, good. So let me now talk about some realizations and some generalizations, and I'm going to focus on two main things. The first is the surface states of topological crystalline insulators. It turns out that these, at least along a particular surface, has the structure that we need for ZQO physics to occur. And I'm also going to generalize to 3D, and there I'm going to talk about some interesting physics regarding wild semimetals there. So if you look at the 001 surface states of topological crystalline insulators of this class, which includes, say, tin telluride, and here I'm plotting everything using the parameters for tin telluride. So it was derived in this paper by Liu, Duan, and Fu that the band structure, the surface state, take Hamiltonian, effective Hamiltonian, takes on this simple form where you have these two terms, which gives you two Dirac points located at 0. And you have this term, which shifts the two Dirac points away from 0. So with just the first three terms, you have a Dirac point here, which describes this Dirac point here. You also have another Dirac point here, but then these two dispersions, they sort of meet at a circle here. And when you turn on this delta term, that turns this circle crossing into two Dirac points located at 0 energy. And if you look at the energy contours for this dispersion, just for the band near 0, it looks like this. You have your Dirac points at 0 energy, and again you can see that there's sort of a peak at 0 That's where this Dirac point is. And so the optimal tunneling trajectory, like before, is going to try to avoid this center part. It's going to go above it or below it. So like before, we now have two conjugate tunneling paths. There's a little bit of extra stuff going on, which is that there's like a Dirac cone here at non-zero energy. And so the Berry phase you get from these two paths, you get an extra pi Berry phase, but that just means that your oscillations are going to be shifted slightly. Right, and these are plotted using tin telluride parameters from this paper in 2012. So let me just put this model in a magnetic field. What you find is it also shows a serpentine Landau fan. You have this square root of B dispersion at low field, and as you get to higher field, you can begin to see that these states at 0 energy are actually oscillating about each other. The crossing points can be solved exactly, actually. And you see that they're always there. So in our earlier model, we had this parameter V, and if V went beyond a critical value, these oscillations actually disappeared. But in this model, the magic fields are always there. You always have these oscillations. Now the magnitude might be exponentially small if you're in the wrong parameter regime, but they're always there in principle. Right. So the oscillation magnitude here goes as e to the minus b star over b, where b star it sets the field scale for this exponential damping, and that's quite a large field. It's 50 Tesla. And you can ask whether these oscillations are actually potentially measurable. So if you look at the magnitude of this oscillation and say plug in 15 Tesla, that gives you a gap of around 0.1 MeV, it's around 1 Kelvin, which is potentially measurable in experiments. But also these parameters in the model, M and delta, which are crucial in determining the magnitude of these oscillations, are also tunable by strain. So by straining the material, it's possible that you could go between regimes where you have strong oscillations and to weak oscillations. And the oscillations will depend exponentially on these parameters. So it could serve as a very important, very sensitive probe for the parameters of these surface states.
Can I ask a question?
Yeah.
Sure. Thanks. So, you know, in this situation, you figure there's probably also some bottom surface states as well, since you can never isolate just one surface.
Yeah.
How much does the picture get messed up by having sort of independent details on the top and bottom surface?
So, I mean, if they're well isolated, or you have some way of measuring properties of only one surface, then everything should hold. I mean, unless your sample is thin enough that these two surface states are talking to each other, I think it should just be that they can be treated as isolated.
But would anything you measure, how would you sort of how would you rig up a measurement in this kind of scheme to isolate just one surface?
Yeah, I mean that's a good question. I mean, you could do like resistivity if you have a sample that's nice, that's nice enough that you can isolate things going on at a surface. So like if you only contact the top surface and you can run current through it and do measurements, and you're sure that there's no bulk contribution, then in principle this should be possible. But I'm not an experimentalist, so I don't know the feasibility of this.
So I was just wondering if you considered it. Thank you.
Mm-hmm.
Thank you.
Yeah, thanks for the question. Okay, now let me finally go to 3D. So there's a very straightforward generalization to 3D, which is we just have the same model, except now there's p z squared term in here. We have a velocity term as before, but now we have an extra vz, pz, sigma z term. And as long as one of these vy's or vz's are small, then we expect to see this ZQO physics. And one place that this type of model might arise naturally is in a weakly gapped nodal ring semimetal. So if you turn Vz equals to 0 or Vy equals 0, then you have a nodal ring protected by some symmetry, and maybe you can consider weak symmetry breaking or some weak perturbation that gaps out this nodal ring into two Dirac points. That gives you a very natural scenario where you have two Dirac points that are connected by some low energy ring, and there's going to be some interference between these two paths of as you go from one ring to another, I mean, from one Dirac point to another. And in this particular model, if we just apply a field in the z direction, this just reduces to the 2D Hamiltonian for each pz. Pz is a good quantum number, except now you have a mass perturbation term here, which gaps it out. And you also have this p squared term here, which just renormalizes your value of delta. So what happens is that you have E equals 0 states, and they exist at the same magic fields at pz equals to 0. And these actually correspond to perfect bulk chiral states of the Weil semimetal. So the phrase I want to highlight here is that we have quantum oscillations of the chiral anomaly. And let me tell you what that means. So if we look at the dispersion, the energy as a function of pz at various magic fields, this is what we find. So we sit at magic field B1 here, the first magic field. we have two exact chiral states. This one is sort of the state, the zero energy state that we solved. This is the other one, and they disperse along one direction only each. If you go between the first and the second magic field, this would be 1.5, say. Now there's a gap between the two. So you no longer have chiral states. They're not perfectly chiral. They look chiral if you're up here, but then as you get down here, you see that there's actually a gap, and you mix between the two states. Now, as you increase field further, you go to B2, the second magic field. Again, you have exact chiral states. Increase field further, another gap opens up. Go even further, increase field. Now you have, again, perfect chiral states. So as a function of magnetic field, we have periodic revivals of these chiral states, and along with that, all the signatures of the chiral anomaly that we associate with these chiral states. In particular, one possible way to probe these would be, say, we know that these wild nodes in the bulk lead to Fermi arc states on the surface, and they're connected via bulk states. So in a magnetic field, what happens is that electrons, they enter the material. As they move, they feel Lorentz force. They move along the Fermi arcs of the surface. But at some point, they reach the end of the Fermi arc, and there's nowhere to go except into the bulk. So they enter the bulk chiral state. They continue all the way to the other side of the sample, and they go back the other direction, and then they traverse the bulk. And this leads to electrons moving in a macroscopic orbit, where you go along the top surface, and then you have to traverse the whole sample, and you go back, and then you traverse the whole sample again. And this leads to quantum oscillations away from EF equals to 0. And this was shown by Potter, Kimchi, and Vishwanath in 2014. And this picture assumes perfect bulk chiral states. So let me just so one possible setup we can have is here. We just have a slab of a material of this material, and we just attach some leads to it, and then we can ask, suppose we put a current in the top lead here, what happens to it? Where does it go? Or rather than putting a current, let's apply a voltage to here and ask what happens. So at small b, what happens is that this voltage, it just directly couples to the current in the Fermi arc states, and you just directly flow along these Fermi arc states, and you exit this other lead in the top surface. So this is a projection onto the YZ plane of this picture. But if we increase field, now if we're at large B, what happens is that the current goes in, it enters the Fermi arc state, it's moving along, but because of the field is large, it gets pushed along the Fermi arc, and at some point it's going to reach the end of the Fermi arc and get transferred into the bulk state. And then it goes across the whole sample, and it comes back out and leaves through the bottom lead. So at large field, if the chiral states are perfect, we expect the current, rather than going out here, it'll prefer to go through the bottom one. Right. So here now let's consider the case where the bulk states are not perfect. So if we're at the magic field, again, the chiral states are perfect, we get what I just showed you. But away from the magic fields, there's now scattering between chiral states. And so what happens is we initially have the same behavior. Things go along here, along the surface state, and then they eventually turn into the bulk due to reaching the end of the Fermi arc. But once they're in the bulk, they realize that these states are not perfectly chiral. They can scatter to one that propagates back up, and eventually they'll turn around, and you end up with no current flow that actually leaves the sample. The current in this case that goes in here and out here will decay exponentially as you increase the system size in the z direction away from the magic fields. If you're at the magic fields, these states are perfect, and so you always end up going to the other to the other side. So here's just some numerics. I just did this. So I'm considering a Lx equals 200, Ly equals 100, and Lz variable. And I'm looking at the current that's coming out of the third lead as a function of magnetic field. So at low fields, you don't get any current that's coming through here, that's coming out here. It's all going in and coming out through the second lead. But as we increase field, the amount of current coming out from lead 3 increases. And at a certain point, you start to see very strong oscillations where at the magic fields, which I've labeled by these black lines, you get a constant, you get some current that's flowing through. But away from the magic fields, you see that as I'm increasing the size of the system in z direction, that it's just going down exponentially to 0. So this is just one possible measurement you can do that would show very clear signs of this quantum oscillations of this chiral states. There's many more possible measurements you could do that would all show oscillations as a function of field. This is just one possible measurement. All right, and that's it. Let me just quickly conclude. So we've identified a new mechanism for quantum oscillations in Dirac semimetals. And these are driven by the serpentine motion of just a single pair of Landau levels. And we sort of showcase this by exact solution of this very special model. And this physics is really driven by destructive interference of 2 different tunneling paths between these 2 Dirac cones. And hopefully I've shown that this leads to a wealth of new quantum oscillatory physics in 3 dimensions. Thank you.
All right. Thank you, Trithep. Very beautiful work and very elegant solutions. Now we have time for questions, so feel free to unmute your mic and ask directly to the speaker, or you can post a question on the chat. I'll read it for you. I think everything is pretty clear. I just wonder, what would be the effect of temperature on the possibility of observing these oscillations?
Right. Yeah, so you want the temperature. I mean, if the temperature is smaller than this, the magnitude of the oscillation, then you expect to see it very clearly. And as a function of temperature, you can probably deduce what the oscillations are doing, right? From this temperature dependence, you can get quite a bit of information. If you go to too high temperatures, then there's a possibility of drowning out all the oscillations. But yeah,
right.
So you don't want to go too high, but low enough, you should be able to see a lot of physics.
I would be curious to hear what about the disorder. If you go back to the standard 2-dimensional situation, where like as simple as it gets, and you clearly showed it's an interference phenomenon, and yeah, is it washed out by disorder in a solid state realization, or you said you did some numerics with disorder. Have you investigated that more systematically?
Yeah, no, we have not estimated. We have not investigated it more systematically. So I don't know. I mean, we did numerics with disorder, and that sort of smoothed things out. But we have not done like a systematic analysis of exactly what disorder does, and if there's a point where you have too much disorder or not. Yeah, that's an open question.
But Trithep, if I can chime in,
Yeah.
with disorder, I mean, it's just as bad as any other quantum oscillation phenomenon, right? Because the figure of merit is whether you can complete an orbit. So there's an effective cyclotron scale, and if your, omega c tau is, much bigger, if tau is big enough that omega c tau is much bigger than 1, you're probably safe. So it's no more fragile, I think, than any other quantum oscillation phenomenon. People have been remarkably successful in seeing other ones, I would say.
Yeah.
Level. Yeah.
I
Because
agree.
all quantum oscillation phenomena are interference phenomena one way or the other. So
Yeah.
Okay, thanks.
A question?
Yes.
Yes,
So in this 3D case, so if I understood correctly, I might have missed it. So your assumption there was that you have two Dirac points, two wild points with the Fermi level just exactly at those
Yes.
points. Now, of course, if you have impurities, you can shift the Fermi level. Also, in typically you have more. In many cases, maybe you have multiple wild points that may not be exactly at the same energy, and therefore the Fermi level may not be exactly at the Weyl points. I'm wondering what are the restrictions that you have, and how does that apply in real materials? To what extent are you limited by that?
So I mean, so the physics itself, right. So I mean, if we want to see these oscillations, we really want to be at we really want the points to be at the Fermi energy. If they're slightly shifted, then yeah, I'm not sure. I'm not sure what would happen in that case.
I think some level of doping shouldn't matter, right? Because the point is that at some level, you'll still absorb into the Fermi arc, go through the bulk, and you'll turn back around, because that's just happening. It just happens below the Fermi energy rather than exactly at it. But the fact is that the chiral conduit is switched off. So I think it should probably survive some level of doping, as long as you don't start mixing in too many of the higher bands. But some fraction of the current will always be carried there. So there'll be some background of the current that's carried in other states, but I suspect some fraction of the current will always go through this channel and make it across to the other side.
Right, and with disorder now, you don't have these perfect chiral states anyway, right? There's always going to be scattering between them. So
there'll be some correction, but
yeah.
all right. Any other questions? Bert, your hand is raised, but I suppose
Oh,
to answer your question.
I just didn't put down.
No problem. So I guess if no other questions, I mean the talk was very clear and easy to follow. So and the very elegant treatment. So I suppose we're all able to get the idea. All right. Thank you so much, everyone, for attending, and we'll meet you again next week. Thank you, Trithep, for joining us today.
Thanks for inviting me.
Goodbye.